Okay, so far we've focused, in terms of solving recurrence relations, we've focused mainly on first order linear recurrence relations. So now we're going to talk a little bit about second order. And the kind of a very standard example of this is the Fibonacci sequence or the Fibonacci recurrence. So remember Fibonacci numbers, you've got 0, 1, 1, 2, 3, 5, and generally if I take the nth term, it's the sum of the previous two terms. So this one will be 8, and then 13, and so on. So the Fibonacci sequence, or the Fibonacci numbers satisfy this recurrence. The nth one is equal to the n minus 1th plus the n minus 2nd, or whatever, n minus 2th. It sounds weird to say n minus 2th, but okay. So how do we solve these things? Yeah, so originally when I was writing up these notes, I wanted to give you a full derivation of how you come up with, the method for solving these things. I might still give that to you later. So using generating functions, it depends on how much time we have. But I decided to start off with, what I should tell you is basically what is the answer to how you solve these things. And later, if there's time, I'll tell you why this method always works. But let's talk about the method, because on an assignment or on a test, you're not going to have to derive the method. All you're going to have to really do is apply it. So let's work out how to apply it. Okay, yeah, and this is what I just said. Okay, so we're going to require the following definition. So if I give you a linear recurrence relation, remember what linear means is that you can write an as some number times an minus 1, something times an minus 2, down to something times an minus k. And we say that it has order k if the constant ck is not 0. So that's what order k means. That basically it's a order k if an depends on the previous terms. It depends on the k previous terms. So second order is like Fibonacci. Fn depends on the two previous terms, so then it's second order. So the characteristic equation, so I should have an equation here, not just a polynomial, so you write it as x to the k. So kind of think of your an as corresponding to the x to the k term, minus c1 x to the k minus 1, c2 x to the k minus 2. So these are all minus, so don't forget the minus sign, all the way down to ck x to the 0, or in other words, x to the 0 is just 1, so this is just ck. And then, so maybe I guess this polynomial here I might refer to as like the characteristic polynomial of the recurrence relation. So when I say the recurrence relation, I mean this one. And the characteristic equation is setting this equal to 0. And notice here I've got this f of n. So I'm not assuming that this is a homogeneous equation. So there could be some other term here. But when I write down the characteristic equation, I ignore that extra term. Okay. So is it clear what this? So I'm defining this in general, but pretty much we're only going to use it for order 2, in which case it's just a quadratic equation or quadratic equality. Right, so like I was just saying, so suppose I have this relation of order 2, where I say an is c1 times an minus 1 plus c2 times an minus 2. Then the characteristic equation, so if I use the previous definition, I just take x squared. This x squared kind of corresponds to the an. So you should think of these as being like, this is where the x squared comes from, kind of. I write a minus c1x corresponding to this. Don't forget the minus sign. And then a minus c2 corresponding to this. And then I write that equals 0. And the roots of the equation, so this is a polynomial. It's some sort of there's some solutions to this equation, and that'll be the roots of the polynomial. And I call those the characteristic roots. And basically, the way that these problems work is that the solution to the recurrence relation, or the general solution specifically, is going to be it's going to depend on the characteristic roots in some kind of natural way. So can anyone tell me, so just to get a bit of practice, so what is, if I give you this and I ask you, what is the characteristic equation? What is it? So everyone's scrambling to write in the chat, I guess. So what is my characteristic equation? So it's good. I'll give you a hint. It's going to start with an x squared. Yeah, a bunch of answers coming in all at once, and all of them are right. So yeah, I think essentially okay, so technically I'm asking for an equation here, not the polynomial, but I mean, in some sense, I'm probably going to get that messed up as well as we go on. So yeah, anyway. So really the thing I'm testing here is, do you remember the equals 0 and do you remember the minus signs? But everyone who answered got that right. Now the characteristic roots are just what you get by kind of solving this quadratic. So if I take, so what are the roots here? I mean, if you kind of look at it, you can see that this factors as x minus 3, x minus 2. If you didn't see that, then you can always apply the quadratic formula. So the characteristic roots are x equals 3 and x equals 2. Okay, right. So what I said before is that if you have your recurrence relation of order 2, linear recurrence relation, and let's assume it's homogeneous, then basically the roots can be used to determine the general solution. So there's three different kind of cases. So you'll probably remember this from high school or something, when you were solving dozens of quadratic equations, that there's three cases kind of. You have the equation could have two different real roots, so distinct real roots. It could have a repeated real root, or it could have no real roots. And the solution to your recurrence relation is going to be a little bit different depending on which of these three cases you have. So let's start with the first one, which is the simplest one. So if the equation has two distinct real roots, so when I say that it has two distinct real roots, I mean that it factors like this. So it factors like x minus r1 times x minus r2, where r1 is not equal to r2. So kind of like the example we had before, when it factored like x minus 3, x minus 2. And then, so the general solution is just like this. It's just an equals some constant a. So a and b are unknowns. So in the general solution, so here's the thing. If you have a general solution to a second order recurrence relation, so okay, thinking back to the first order ones, when you have the general solution, they usually have just one unknown, which is usually just like a0. When you have a second order recurrence relation, you usually have, if you look at the general solution, it has two unknowns. And generally with order k relation, the general solution will usually have k unknowns. Okay, so the general solution is just that an is equal to some number a times the first root r1 to the power n plus b times the second root r2 to the power n. And so it's actually pretty quick to get from the recurrence relation to the general solution. All you do is you just take your characteristic equation, find the roots. If they're different, you just write this down. That's the general solution. That's the end of it. The place where there's a little bit more work is if you want to find a particular solution. So if I've given you some initial conditions, let's say I say a0 is 1 and a1 is 7, then you need to plug those values in. So you need to plug in the value 0 everywhere and plug in the value 1, and that'll give you some way of computing a and b. Okay, so we'll see some examples later, but okay, so here's our second case. First of all, are there any questions about this case? Or are we okay? Okay, I guess not, but we'll see examples. So if you don't get it, then hopefully those examples will help. Here's one which is weird, and yeah, this one you need to kind of remember how it works. So suppose now that the characteristic polynomial has a repeated root. In other words, it factors like x minus r squared. So for example, it's like x minus 7 squared or something. Then your general solution is going to look a little bit different. So it's going to be that an equals a times r to the n plus b times n r to the n. So this is the part that you should not forget. If you just write b r to the n, things are going to go wrong in most problems that I give you. So you must remember this general solution, that there's an n here. And so I'm, like I said, I'm not giving you the full derivation of why this works, but it's sort of related to how partial fractions work. So if you don't get this, perhaps don't be confused. But the reason you have this n is kind of related to the fact that when I do partial fractions, you have to split this up. Maybe if I have anyway, the fact that you have to involve the squared thing. And basically when I take 1 over 1 minus x squared, it looks like n x to the n. And kind of this n is sort of why you have this n. But perhaps let's not dwell on that too much. For the purposes of solving most of the problems, what you really need to do is kind of just remember that this is the solution. And again, if I give you some initial conditions, then what you want to do is plug them in and solve for a and b. Now here's another weird one. Suppose that you don't have any real roots. So for example, if I took if I took the equation like x squared plus 1 equals 0, this has no real roots. But you can, so actually maybe I should ask, probably you're not that familiar with complex numbers, maybe, right? Has anyone seen complex numbers before? Or are you comfortable or uncomfortable with complex numbers? Okay, so some of you have seen it before. Okay. In any case, so suppose, I give you some sort of, you're given, you get some sort of quadratic equation or quadratic, equality. So some quadratic thing equals 0. Remember, so one thing to always remember is if you're having a hard time getting the roots, use the quadratic equation, right? This whole thing about that the solution is b or negative b plus or minus the square root of b squared minus 4ac over 2a, right? This whole, if you have ax squared plus bx plus c, right? Sometimes the thing under the square root will be negative. And so what you get is two solutions. You'll have two complex roots, which look like, the first root will be some real number s plus ti. So these are s and t are real numbers, and t is not 0. And you'll have another root, which is r2, which is s minus ti. Okay, if you plug, if you think of how this works, those are always going to be what your roots look like. And actually the solution to this one is kind of similar to the first case. So, I'm only kind of talking about it because separately because people might not be that comfortable with complex numbers, but the solution is actually the same as the initial case. You just take a times r1 to the n plus b times r2 to the n, where your r1 and r2, they're complex numbers, but who cares? That's fine. And again, if I gave you initial conditions, you just plug it in and you solve for a and b. Okay. So any questions about any of these cases or anything so far? If not, let's let's do a nice example. So I've talked a whole bunch of times about Fibonacci, but we haven't solved it yet. So now we have the tools to solve it. So I take the Fibonacci recurrence. Fn is fn minus 1 plus fn minus 2. And so I want to solve it using the facts that I've given you so far. So the first step is to just write down the characteristic equation. So maybe I've set this up as a poll. I'm not sure this, anyway, so let me, so if you know the answer, then let's maybe try to be quick here. So what is the characteristic of this quadratic, this second order recurrence relation? Fn is fn minus 1 plus fn minus 2. And we're getting a whole bunch of answers kind of converging on the same thing. So maybe this was too easy of a poll, but I'm happy to see that that we're getting the right thing, which is, remember what you do is you take kind of corresponding to this, you take a x squared, corresponding to this, you take so remember the minus sign, so minus x here, and then this corresponds to a minus 1. If you wanted to, you could think of, it might be more natural to think of, if you want to get the characteristic equation, and if you don't want to forget minus signs, just write everything on the same side, right? If you prefer. And then it's pretty natural then to just say, okay, you have to remember which way it goes as well. Like don't write this as x, because this has a 2 in it. Maybe you might be confused to write that as x squared or something. But as long as you just keep it straight that the biggest one here corresponds to x squared, and then x, and then x to the 0, which is 1. Okay, so that's our answer. So, okay, so what are the roots? So any ideas how to get that? So when I look at this, I mean, does anything jump out at you for the roots? Yeah, I would just go for the quadratic formula. I mean, it's always a safe bet, because, okay, maybe sometimes you'll have an equation where you can just see the roots. Like it's just like, this one we had before was pretty easy, like x squared minus 5x plus 6. I can sort of see the 2 and the 3, or the minus 2 and the minus 3, whatever way you want to think of it, sitting there. But here, it's nothing jumps out at me. So I may as well just use the quadratic formula. So I get my 1 plus minus square root. So the 1 is, yeah, if I wanted to write this as, oh, well, I guess people know the quadratic formula. So b squared, which is 1, I'll just write 1, minus 4 times 1 times minus 1 over 2 times 1. So I've got 1 plus minus square root 5 over 2. And now I'm glad I did the quadratic formula, because I wouldn't have ever guessed this by just looking at it. So those are our 2 roots. So now the general solution, we've already got the general solution. It's that easy, like it's that quick. So the general solution just looks like this. It's fn is of the form some number a times our first root to the power n plus b times the other root to the power n. And here, remember, it's important that the roots are different. If I had a repeated root, I would have had to do something different. But so this is the general solution. That's the end of it. Let's now go a little bit further, though, and compute a specific solution with some initial conditions. So, right. So if I take, so my, the usual Fibonacci numbers, they start with, well, it depends where you want to start them, but the way I've been defining them is that they start with 0, and then 1, and then 1. So that's like f0, f1, f2, 2, ... So let's solve this with respect to those initial conditions. So this is our general solution. And like I said, to get a particular solution, all you do is plug things in. So, and then do some algebra. So if I plug in 0, then I've got a times this blah, blah, blah to the power 0, b times some other blah, blah, blah to the power 0. I don't really care what the blah, blah, blah is, because anything to the 0 is just 1, except you might have to be careful if I've got a 0 in here. 0 to the 0 is not defined. So don't write down 0 to the 0. But anyway, so so here we've got, this is just 1 and 1. So we have a plus b. And f0 is 0, so I have a plus b equals 0. And then if I plug in 1, so I've got f1 is 1, and f1 is equal to a times, this thing, b times that thing to the 1, which is going to be, so a plus b over 2, isn't it? Because if you put the a inside here, you can see that you get a plus b here, and you have a in front of the root 5, and the b in front of the, a plus b over 2, my bad. There's no cancellation there. I should just do this a bit slower. So a plus b plus root 5 times a minus b over 2. Is that clear? How I got that? This is just algebra, but yeah. Okay. So actually here, I've kind of not done that calculation I was messing up with. So here I've actually just left it as a times this thing, b times that thing, without doing this step. So let's just kind of go with that. So the first equation, so a plus b equals 0, this came from f0, right? So this implies that b is negative a. If I kind of plug this in to the second equation, so instead of a b, I'll put a minus a, I get this. And now if we think of what happens, you do get some cancellation. So I have a 1 times a here. I've got a 1 times minus a, so those are going to cancel. I've got an a times root 5. I've got a negative a times negative root 5. Those are not going to cancel. Those are going to add up to a 2 root 5 on the numerator. Anyway, so what you get is then that basically a times root 5 is 1. Or in other words, a is 1 over root 5. Okay, and then b is negative 1 over root 5 because of this equation here. So this gives us a solution to the Fibonacci numbers. So the nth Fibonacci number, believe it or not, is equal to 1 over root 5 times 1 plus root 5 over 2 to the n minus 1 over root 5 times 1 minus root 5 over 2 to the n. Does this seem bizarre to anyone else? Because, so the Fibonacci numbers are integers, right? It's 1, or 0, 1, 1, 2, 3, 5, 8, 13, 21. So somehow by computing this, very irrational looking expression, it always gives you an integer, which is kind of neat, I guess. And so I think, to be honest, I think this is quite an unexpected solution. Like this is, this is the Fibonacci numbers. And if you did check the recurrence, it'll work. So maybe I won't do that right now, but it will work. Have people heard of the golden ratio? So this is some funny, interesting thing that like turns up in, it turns up in nature everywhere. If you look at like whatever shell of some, I don't know, snail or some sea creature or something, you look at a bunch of ratios, or you look at the ratio of various parts of the human body. For some reason, those ratios are usually around this golden ratio. And kind of magically here, you've got this golden ratio showing up in the Fibonacci numbers. So yeah, the golden ratio is 1 plus root 5 over 2. And this is just, so phi is the golden ratio. This is just phi to the n minus 1 minus phi to the n over root 5. Which, okay, this is not officially part of the course. You don't need to memorize what the golden ratio is, but this is kind of a cute thing that happens. So let me, let's just kind of keep doing examples until time runs out, I guess. I don't really have anything else to talk about today. So it's good, but it's good, I think, to get more experience with this. So suppose I let an, so I've got the recurrence, an is negative 4 and an minus 1, minus 13 an minus 2. So we've now practiced this a few times. What's the characteristic equation? And you can see it's x squared plus 4x plus 13. Now, sorry. Again, if we use our trusty binomial, or sorry, what do you call it? Quadratic formula. You have negative 4 plus minus square root of 4 squared minus 4 times 1 times 13 over 2, which, okay, I guess you can take my word for it. At least I hope that this equals this. So negative 4 plus or minus the square root of negative 36 over 2. So everything over 2. 4 times 13, it comes out to like what? 52. Yeah, 16 minus 52. That sounds like 36. Negative 36. Okay, so this is one of these situations where we have no real roots, right? This is a complex number. You cannot, in high school when you learn about quadratic equations and stuff, they tell you cannot take the square root of a negative number. But we're going to do that, right? So what's the square root of negative 36 in terms of like I or whatever? Well, the way that square roots work is that this is the square root of 36 times the square root of negative 1, right? I guess we all remember square root of 36 is 6. Square root of negative 1, you just write it as I. So this thing here you can just write as 6i. So this is, So if I put in a 6i here, I divide everything by 2, I have a negative 2 plus or minus 3i, and that's it. Those are the roots. Okay. So from that point, you can just write down the general solution. It's, kind of game over in that sense. So the general solution is a times negative 2 plus 3i to the n, b times negative 2 minus 3i to the n. Okay. So now suppose we had some initial conditions. What do I have here? Sorry, there's some typos here. So suppose I told you that a0 is 2, a1 is negative 4. So you just plug things in, right? You write 2 is a0, but also a0 is this, because that's what our formula says. So we get a, this thing to the 0, that thing to the 0, anything to the 0, except be careful about 0, is 1. So got a plus b here. A1, you have -4 equals, raise these things to the first power. And if you think about it, oh, no, so I've messed up a few things here. So that should be a -3i. And somehow so maybe let's ignore what I'm saying here. Or wait, no, let's ignore this for a second. So this should be -2a plus -2b plus 3i times a minus 3i times b. So this is a minus b times 3i. Okay, so if we're going to have 4 equaling this, so what I wrote there is correct, but what I had written here was not correct, right? So for some reason, I just didn't write down the imaginary part. But here's the thing. So if 4 equals this, then that means that the imaginary part here needs to be 0, right? So we have to have a equals b, right? Because I have to get a 0 here. And once you know that a equals b, you can kind of look at your first equation and say 2. So b is just a, so 2 equals 2a, right? Or maybe I'll to do that in 2 steps, a plus b, but b is a, so this is equal to 2a. So that implies that a equals 1. And so b equals 1 because they're equal. And so that's my particular solution in this case. Okay. Oh yeah, here's the thing. So, maybe I won't worry about that. So I was just kind of thinking, if you wanted to check this, or if you wanted to, there's something does feel weird about this, right? That my general solution, or my particular solution, we said that it's this. Like this was our particular solution we computed on the next slide. It again, like remember with the Fibonacci numbers, it feels weird that these very irrational looking numbers end up being integers. This feels weird too, right? I've got these imaginary numbers, or these complex numbers, which end up, when you kind of take the powers of them, they end up being integers. It turns out it's not actually that weird. Because in some sense, if you take the powers of these things, the imaginary parts are going to cancel in some natural way. But maybe I won't go too deeply into that. But just something to keep in mind is that this is, for every n, this is going to compute an integer, even though it doesn't really look like it. Because you can use things like, if you have a I squared, you can just replace that by -1. And somehow, magically, the imaginary parts are all going to cancel. If you suppose I plug in n equals 4, you expand everything, you'll see that the I terms cancel. So maybe let's do another example. So by the way, so next time what we've been doing today is I've only given you some homogeneous second order equations. What we're going to do past, in the next lecture and possibly the one after that, is look at how to solve the, more complicated equations. So for example, a non-homogeneous second order equation using generating functions. So this is going to bring together kind of all of these things we've been doing on generating functions, recurrence relations, and everything like that. Okay, so let's just, let me do another example. So suppose I take an equals -2 or -4 an minus 1 minus 4 an minus 2. So, okay, characteristic equation, x squared plus 4x plus 4. We can factor this, but here we've got this situation that this is x plus 2 squared, right? So this is a repeated root. So what should I write down as my general solution here? Anyone? My general solution, I think it had a bn in it. It's going to have a bn for sure. Yeah. First of all, my root here, not quite. So my root is -2, right? What you do is you take the root of the root of my, whatever, if I write this equals 0, the solution is, my repeated root is -2. Yeah, exactly. So a times -2 to the n plus bn -2 to the n. So you guys are going to get plenty of practice with this, on the assignment and stuff. Actually, well, I should say that's probably not enough practice. So if you want to be good at this for the test, I would probably just do, these things actually don't take that long. So just do like 10 of these things and you'll kind of, maybe you'll get the idea before then, right? But yeah, thinking through how you do this yourself is kind of important. Okay. And again, so that's the general solution. That's the end of it. Like you don't have to do anything more than that to get the general solution. So it's all about just writing down a quadratic and solving it. And then just remembering the format of the answer, basically. Now, right. Now, if you wanted to get some particular solution here, if I told you that A0 is whatever and B0 or A1 is whatever, you just plug in the values. Well, maybe let's do something like that. So let's suppose I give you that A0 is 3 and A1 is 5. By the way, so when you're doing maybe I'm not sure if I've given or if I've emphasized this enough, but when you're doing a second order thing, you should expect, if I want the particular solution, you should expect to get 2 initial conditions. And the reason is because your general solution has 2 unknowns, right? So in order to get the value of those 2 unknowns, you need 2 initial conditions, okay? If I have a first order equation, you're going to get just 1 initial condition. Okay, so if I do my A0 is 3 thing, I just plug in zeros everywhere. So I start with a 3, I'll write A0, plug in zeros, and I get A. And this is a good thing. I like this n because that just makes everything 0 here. So A plus 0. So that actually just tells me that A is 3 right off the bat. A1 is 5, so that tells me that A, which I know is 3, but I'll do that in a second, times -2 plus B, B times 1 times -2. So it's just B times -2. So I'll plug in my A now. So 5 is equal to -6 minus 2B. So 5 minus 6 is 5 plus 6. I really shouldn't, Anyway, so B is -11 over 2. Okay. Now here's the thing. So another thing I should maybe highlight is for whatever reason, I seem to usually be giving you the initial conditions for A0 and A1. I don't have to give you those. I could give you different initial conditions. So for example, I could give you A1 and A2. If I was trying to do something really weird, I could even give you some other initial conditions which aren't consecutive. I could give you A0 and A2. And you need to be able to work out A and B given that. But it's just plugging in the values and doing the algebra. But yeah, so don't be, if I give you the initial condition A for A1 and A7, for example, don't be too confused by that, because again, all you do is you plug in n equals 1 and you plug in n equals 7. So it's hopefully not too bad.